In this video I'm going to talk about the adjacency matrix of a graph and the connection between the powers of this adjacency matrix and the number of paths between vertices in a graph of a given length. So first, this is basically the definition. So the adjacency matrix of a graph is a matrix where all rows and all columns correspond to vertices. So all of these correspond to vertices, both columns and rows, and the value at the value in the row corresponding to vertex u and the column corresponding to vertex v. So like we denoted by a with the index uv, so auv. So it's either 1 or 0 depending if u and v are adjacent. So if u is adjacent to v, so like it means that if there is an edge from u to v, so there is vertex u, there is vertex v. If there is an edge from u to v, then this is equal to 1, and if there is no edge, then 0. So basically now the main result that I'm going to talk about today, theorem that says that for any n, so the power of the matrix A, so A to the power n, consists of the numbers that indicate the number of paths between the corresponding vertices of length n. So specifically the value in this matrix in the row corresponding to vertex u and a column corresponding to vertex v. So what in the original adjacency matrix was this 0, 1 or 0 indicating the adjacency. So in this a to the power n, the value for the vertices u and v is equal to the number of paths between u and v of length n, the number of paths of length n between u and v. So okay, so basically we are going to prove it by induction. So by induction, on n, of course. So the base case for n equal to 1 is trivial. So when n is equal to 1, this is the original adjacency matrix, and so A and the value at for the vertices u and v, like in column u and in row u and column v, is equal to 0, 1 depending if it's adjacent. So exactly this definition. So zero or 1 if u is adjacent to v, and 0 otherwise. And notice that this is exactly equal to the number of path of length 1 between u and v. Because path of length 1, this is an edge. So path of length, because path of length 1, this is the same as an edge. So this is basically what it's saying, is that this is equal. So this is equal to the number of edges between u and v. But the number of edges, like it's not a multigraph, it's a regular graph. So between u and v, either there is an edge or there is no edge. So it's either 1 or 0, depending if u and v are adjacent. And this is exactly this. So the base case holds. So now, like actually we don't need to consider separately the case of n equal to 2, but I think it would be kind of instructive to understand why this statement holds. So it's just for illustrative purposes. It's not actually necessary for the proof, because induction works without considering n equal to 2, but it's very useful to understand the theorem. So when we have n equal to 2, so basically so a squared, it's basically a multiplied by itself. So what is so how we multiply two matrices? So we take a row, so we have two matrices. This is, each of them is matrix A. So we take a row for vertex u and a column in this matrix for vertex v. So the result of the multiplication, it would be so the value in the resulting matrix, so this would be a squared. So in the resulting matrix, at the intersection of the row u and column v, so this value here, like to calculate this value, like we need to take the row in the first matrix for vertex u, the column in the second matrix for vertex v, and multiply these two vectors. So basically the first value in this vector multiplied by the first here, the second by the second, and then sum of these products together. So basically, to write this another way, so if we have here the vertex x and here vertex x, so we take the column for the vertex x, and here we take the row for the vertex x. So in the intersection, so A, so A ux would be multiplied by A AXV. So this number multiplied by this number, and all of this would be summed for all x. So for all vertices x, we sum all of this, and this would be the value here in the resulting matrix. So this would be the value of a squared at UV, the value in the matrix A squared in the row U and column V. So that's how it's calculated. This is just the standard matrix multiplication, right? So, but notice, so now that this is equal either 1 or 0 depending on if U and X is adjacent. So either 1 or 0 depending of like if 1 would be if U is adjacent to X, or just let's write it more simply. So this indicating like this, this is 0, 1 indicating the adjacency of U and X, and this value is 1 or 0 indicating the adjacency of X and V. So basically the product would be 1 only when both of these hold. So when U and X is adjacent and X and V is adjacent, then the product would be 1, otherwise it would be 0, right? And so now what happens when we take a sum of numbers that are equal to 0 and 1? So the sum of such numbers would be simply the number of those items which is equal to 1, right? So this sum, like this whole sum, would be equal to the number of x for which both of these multipliers is equal to 1. Number of such x that U is adjacent to X and X is adjacent to V, right? So now let's draw a picture. So we have a vertex U and we have a vertex V. So what does it mean that we take the number? So here somewhere is vertex X. So we need to find the number of such vertices X that U is adjacent to X. So there is an edge from U to X, and there is an edge from X to V. So this is simply the number of. So this is simply the number of. So let's write it here. Now, this is the number of X that is a common neighbor of U and V. So the number, we can even drop the name X. So this is the number of common common neighbors of U and V. Right? So this is the number of common neighbors. So let's say this is X, somewhere here is Y, that is adjacent to both U and V. So, but this is also like, this also can be rewritten as the number of paths of length 2 between U and V. Right? Because a common neighbor of U and V, this is exactly a path of length 2. UXV, this is a path of length 2. UYV, this is a path of length 2. So, yeah, so basically we proved the statement for n equal to 2. So now we will just make modifications in what I wrote. So now let's remove that it's n equal to 2. Now we consider n plus 1. So we assume that the statement holds for n. So let's remove this. Okay, so suppose the statement is true for n, I consider it for n plus 1. Consider it for n plus 1. So yeah, so now we have a matrix a to the power of n plus 1, and we represent it as a to the power of n multiplied by the matrix A. So now we write, so this is equal to this product of two matrices. The first one is a to the power n, the second one is a, and here it would be, the result would be a to the power of n plus 1. And so again, we like the multiplication of any two matrices is that we take the row corresponding to vertex u in the first matrix, we take the column corresponding to the vertex v in the second matrix, and we multiply these two vectors and obtain the value at the intersection of the row u and column v is in the resulting matrix. So again, this would be equal to the value in the resulting matrix a to the power n plus 1 in column u and in row u and column v would be equal to the sum of a to the power of n at ux, at row u and column x, and the value in the matrix A at xv. So, and sum for all x. So again, we write that this would be, so the first So the second, so this one is still the same. This is true, but for the first one, this is not true anymore. This is not an adjacency matrix, but this is the a to the power n, and so now this is by inductive hypothesis. By inductive hypothesis, this is equal to the number of path of length n between u and v. Yes, so this is the a to the power n, not u and v, I'm sorry, but u and x. U and x, because this is for vertices u and x. So now our picture should be like this. So we have the vertices u and v. And here we multiply, so the number of paths between u and x, so the number of different paths in the graph between u and x of length n, and the adjacency between x and v. So basically this is the number of path of length 1. So when we multiply these two numbers together, so and then sum for all x, so the result would be the number of x. So when number of such x when both of these values are equal to 1, right? Because if at least one of them is 0, it contributes 0 to the sum. So this is the number of such x that both of them is 1. So the second condition is exactly true as was previously. X is adjacent to v, but the first one we need to replace, not u is adjacent to x, but so this is the number of paths. Okay, it's not. Okay, it's not the number of x. Okay, we need to remove all of this. Yeah, okay, so let's remove the remaining. Okay, so we see that so the first one is the number of paths between u and x of length n, and the second one, so this is not 0 or 1. Yeah, so this is the number of paths. It can be greater than 1. It can be any number. But this is the second multiplier is 0 or 1. Right, so basically there are two cases. So this product is equal to either the number of path of length n between u and x, if so this is equal to the number of path of length n between u and x if the second one is equal to 1. So if x is adjacent to v, so if x is adjacent to v, or it's equal to 0 if x is not adjacent. Is not adjacent to v. So either it's the number of path of length n, so each term in the sum. Either it's the number of path, so either it's this number of path between u and x, if there is an edge from x to v, or it's 0. But notice that the number of path between u and v of length n passing through x. So this is basically equal to the number of path of length n plus 1 of length n plus 1, the last edge of which path, the last edge of which is xv. So you see basically that every path of length n between u and x, this path can be extended by the edge xv, if there is such an edge, to v. And now we get a path of length n plus 1. So we added one edge, therefore the length increased by 1. So now we get a length of n plus 1. It passes through x, but not just passes through x, but this is the last edge of the path. It's not passes through x somewhere in between, but at the last step. The last step is from x to v, right? So, and this holds for both cases. Because if there is no edge, the second case, right? So if there is no edge from x to v, then this number is also 0. The number of path of length n plus 1, the last edge of which is xv. But if there is no edge xv, then there are no such path at all, and this would be equal to 0. This whole number of paths would be equal to 0. So both of these cases hold. Okay, so and now we need to sum all of this. So this was only one term for x, and now we have a sum for all x. When we sum all of this together for all x, for all vertices x, we simply get, so the sum of this of for all x of a to the power n ux a xv is equal to the sum for all vertices x of this, what I wrote here. So the number of path of length n plus 1 of length n plus 1, the last edge of which is xv. So now when we sum all of this together for all x, what we get is basically the number of path, any path of length n plus 1 well, between u and v. Here, I need also to write that it's between u and v. Number of n plus 1 between u and v, and here also between u and v. Yeah, so this is simply the number of path of length n plus, because like any such path, like the last edge of this path, it passes through some vertex. So like when we consider the last edge of this path, here is the vertex v, here is the vertex u. Consider some path of length n plus 1. So it has a last edge somewhere. So the previous vertex before v at this path, we denoted by x, and it should be included in this sum for this x, right? Yeah, so, and this is basically what we needed, because this sum that we evaluated, it was the element of the matrix A to the power n plus 1 at the vertices uv for row u and column v. So this is evaluated as the sum, the standard matrix multiplication. Then by chain of equalities we arrived here that this is the number of path between the path of length n plus 1 between u and v. And this is exactly the equality that we needed to prove. Yeah, so basically this exactly this for n plus 1. So again we assume this is by induction, right? So we are supposed that this equality holds for n, This was inductive hypothesis, and we needed to prove that it also holds for n+1. And this is exactly what we obtained. That this for a to the power n+1 for u and v, the element at u and v, is equal to this. Yeah, so this concludes the proof of the theorem.